Stangibelisco here, proprietor and operator of amateur radio mobile CW station W1GV Whiskey 1. Good vibrations. We just got done in chapter 4 of this sequence with a test of the Yaesu active tuning antenna system versus an 8-foot whip force-fed at the transmitter end with 13 feet of RG58U coax on a frequency of 10 megahertz. Now the key difference between these systems lies in the point where the matching takes place. Here is the transceiver, which is a venerable Yaesu FT857D. That thing connects to the antenna. Here's the antenna, and it connects by means of a feed line which comprises RG58U coax, approximately 13 feet long in the case of the whip and 10 feet long in the case of the active tuning antenna system. The ground for this antenna comprises only a connection to the bed of my pickup truck Big Number 8, which I have tested for continuity with the rest of the vehicle, and it does have continuity, so we have a ground connection there. I outlined all of this in previous chapters here. This is the only place where a ground connection takes place with this system so as to avoid ground loops. But the key here is where the matching occurs. Let me just extend this transmission line all the way to the antenna. Now in the case of the whip antenna, which is an 8-foot whip, a CB whip actually with a foot chopped off of it, so it is a quarter wavelength at 28 megahertz and perfectly matches to the radio without any tuner at all on 28 megahertz, and it is a killer antenna for mobile at that frequency. It's just about as good as you can reasonably expect to get with a mobile system. So that works very well on 28 megahertz, but we were talking about a frequency of 10 megahertz or 10.1075 thereabouts, where I had a contact with Herb WR9H from South Dakota to Illinois on 10 megahertz in the 2 o'clock p.m. my time, 3 o'clock p.m. daylight time, his time. So what I discovered, there are two ways that you can do this. You can have an 8-foot whip antenna and force feed it with a transmatch right there. Then you will have a high SWR on this feed line, but no shortening or no inductor in the antenna. The inductor is in the tuner. Or you can connect up the ATAS, active tuning. Active tuning, okay. Active tuning antenna system by Yaesu. And that has as far as I understand it, an inductor that mechanically tunes by finding the tap on that inductor where the SWR is lowest, and the microprocessor in the transceiver manipulates that and measures the SWR until it dips. It's really nifty. It's really cool. Tune's really neat. So you get a 1-to-1 SWR along there. And although the antenna here is shorter, it's only 5 feet. Well, at this frequency, 10 megahertz, the verdict is clearly in. The ATAS wins. ATAS wins at 10 megahertz. where both antennas are far shorter than a quarter wavelength in free space. Now, I noticed when I received with that ATAS that it received a lot more noise and a lot more signals than the whip, and it apparently transmits a lot more signals too. But as we increase the frequency of this system, as we increase the frequency, we've got two antennas here. We have, on the one hand, the ATAS with an inductor to load it, and on the other hand, we have the whip with no inductor in it. This is 8 feet, and this is about 5 feet. It varies slightly in length as the system finds the best match, but not very much, not very much. So this is the ATAS right here, and this is the whip right here. Whoop! I'm just going to leave it like that. You know, there's something about doing videos and writing on a beige board at the same time that my brain microprocessor doesn't seem to like that. Now, anyway, it's just old. This thing clearly wins at 10 megahertz. This clearly has it. At 10 meters though, at 28 megahertz, I'll bet this thing will beat the ATAS. Because there's a 1-to-1 standing wave ratio on the line without any tuner in there to add any loss. No tuning network anywhere. But what about frequencies in between? How about as we go down the spectrum, increasing wavelength 24 megahertz or 12 meters, 21 megahertz or 15 meters, 18 megahertz or 17 meters, 14 megahertz or 20 meters. I noticed, at least I did a test, I tuned both of these things and listened on 24 megahertz, and they were comparable. Comparable noise, comparable signals. I have not tried 28 megahertz, but I suspect that the ATAS will win at the lower frequency bands, clearly, but its advantage will diminish as the frequency rises, and at some point they will have a tie. So I'm, as time goes by, going to try and experiment and get signal reports from other stations, not just what I hear, but what they hear, and see what happens there. We can go through theory all day long. We can talk about losses, we can make calculations, we can look up graphs and charts and tables all day long, but the thing that really matters here, the point that I really need to emphasize, is what my physics advisor at the University of Minnesota told me way back in the 1970s, after I told him about a weird experiment I did. Well, with Herb and me together, we can say that two experimenters can keep 24 theorists busy. Busy, not by, Stanley. Busy. Two experimenters can, he said one experimenter can keep 12 theorists busy. I'd say it's more like 100 or 1,000 theorists that can get tied in knots when the results of experiments do not agree with their predictions or come as a complete surprise. Stangibelisco W1GV, Whiskey 1, good vibrations. Signing off for now. Listen for me mainly from home on 14 megahertz CW or PSK. So long!